All right, let's get started. So today we're talking about how to measure concept drift and how to measure its impact on model performance. General setup is we're gonna have a model. The model is ready to be deployed. We deploy the model, and sometimes it might happen that the pattern that the model has learned is no longer relevant or applicable. So here, for example, you see in this visualization that the decision boundary between the test set and our production data has changed. So the model needs to be retrained, and we're going to discuss how to go about it. And also, one important thing, we're going to discuss how it actually impacts our model retraining schedule and whether we can use concept drift detection for the actual retraining of the model or as a trigger for retraining, and whether this might be potentially even better than just using the level of performance that your model has to trigger retraining. And the answer is, to spoil it a bit, yes, concept drift detection is actually the best way to trigger your model retraining, and we'll get to that at the end of the workshop. Let's start with the agenda. On the agenda, we have 5 points. First, we're going to open with a very typical thing, which is basically how to actually monitor your models and what is the role of concept drift detection in the general overarching model monitoring flow. Then we're going to discuss the 2 main causes of machine learning model failure, which is the concept drift and the covariate shift. And today we're going to be focusing on concept drift, which is kind of different than most of the webinars we've done so far, where most of the focus was on the covariate shift. But now it's time for the concept drift to shine. Then we're going to discuss our main algorithm that we have invented / discovered, whatever is your opinion on whether you discover or invent algorithms, and which is our main algorithm we use for detecting concept drift. And the way we detect it is we can either quantify the actual magnitude of concept drift, and we're going to define what we mean by the magnitude of concept drift soon, or we can quantify the impact of the concept drift on your performance or on your machine learning metrics such as F1, precision, recall, etc. And then the last and most actionable and arguably most important point is how concept drift can be used to actually trigger automated retraining loop, and how you can actually automate retraining and make sure you train only when it's needed and strictly always when it is needed, which should help you reduce your retraining costs and improve your model performance over a longer time horizon. So let's start with the ML monitoring flow. ML monitoring flow is basically an overarching way of how we see basically users and how we believe that you should monitor your models. It starts with performance monitoring. So basically that means that if you can calculate performance of your models, this should be the main metric that you track when you monitor your models in production. So it's not data drift, but actual performance, such as ROCE you see, F1, MA for regression models, etc. And if you cannot calculate performance, we have a suite of algorithms that allow you to estimate performance even in the absence of ground truth, because if you don't have ground truth or you don't have the target data after you make the prediction, it's impossible to actually calculate the performance. And we've developed a suite of algorithms, including CVP, that allow you to actually estimate the performance. And we have a couple of webinars and other materials. Mafalda will send links in the chat. Then if we see that there is an issue with model performance, so we see a performance drop or performance change that was very strongly unexpected, then we need to go to the second step, which is the root cause analysis, where we basically try to figure out what actually went wrong and how we can potentially resolve the issue. So we figure out whether it's the concept drift that's actually at fault, whether there's maybe some data quality issue, or whether we're dealing with covariate shift, where, for example, simple retraining would not resolve the problem. And then once we've nailed down what actually is the issue, then we can go to the issue resolution and take appropriate steps. And here, for the purposes of this webinar, we're going to be focusing on concept drift, which is mostly useful as part of the root cause analysis, when we can actually quantify the exact impact of concept drift on performance. So if we see a drop in performance, we know how much of that can be attributed to concept drift. And then we can also even estimate how much we stand to gain if we retrain our model, because generally speaking, if you retrain your model, concept drift should go away because the model will now capture the current concept. Of course, this is slightly simplifying, but this is the kind of gist of why you should detect concept drift to use it to quantify whether you should retrain your models or not. Just one more thing about performance monitoring before we move forward. It is really the most important step in the flow because it gives you a direct proxy for the business impact. it generally will not give you false positives, because if performance drops, it means that something is going wrong and that your business impact is in danger, or you might actually already be losing business impact. Whereas if you just monitor, let's say, data drift metrics, it might be that 20 out of your 200 features are consistently drifting, but it doesn't matter because the model generalizes well, even to that drifted data. And it is a trigger, as I already mentioned, for root cause analysis. So this is something that really should be the kind of entry point for the monitoring. And as I already mentioned, we cannot do it easily without the target data. We have performance estimation for that, but that's a topic for a different discussion. So now that we covered this ML monitoring flow and what is the role of concept drift, which is it's a part of root cause analysis. First and foremost, let's delve into the reasons why machine learning models can fail and why concept drift is one of those potential failure modes. So let's start with the basics. And the basics are basic, simple. Imagine that we have a very simple data distribution that only has one feature, feature X. We know that there exists some kind of true pattern in the world that we're trying to predict that maps this feature X to some kind of binary variable that we're trying to predict. So dealing with, for example, with a binary classification setting. So we're trying to capture this true pattern by using machine learning algorithms. We have some data sample. And then if we look at this data that we actually have, we will see that we're going to have certain amount of positive class and negative class in it, like visualized here in the last plot in this slide. But all these parts are dynamic, and once we deploy our models to production, both the true pattern and the sampling distribution, so our data distribution, may change. Let's talk about it. So the first thing that might change is the actual sampling distribution, so the distribution of our covariates, which is just called covariate shift, because covariates change, they shift their distribution. So imagine here, if we look at this part, we have original sample. Once we deployed our model to production, we see that the mean of that distribution has increased, and it's looks different now. That means that if we sample from the distribution, the new distribution, also the actual class balance might change, which means that model performance may or may not be affected. And again, we discussed that in depth in our performance estimation documentations, blogs, webinars. If you're interested in how covariate shift impacts performance, then you're welcome to check those out. Just to define covariate shift a bit more formally, covariate shift is the change in the joint model input distribution. So we look at the joint distribution of all the model inputs. If the joint distribution changes, not even if any specific feature changes, but if this joint distribution changes, so maybe just correlations change, we are dealing with covariate shift. Now, the second potential reason why your models may fail is so-called concept drift. And for concept drift, the sampling, we're going to assume that it stays the same, so there is no change in the covariate distribution, but the true pattern that exists in the world has changed. So before, we had this strong kind of sigmoid pattern, now it became more linear. And if we train our model to capture this sigmoid pattern, but in time, the pattern will change, then the model will actually mispredict quite a lot of observations, and it's going to be quite incorrect, especially here, where a lot of observations have shifted from positive class from negative class to positive, where it should predict, let's say, 0.8, it would only predict, let's say, 0.5. So we're going to see strongly decreased performance, especially if your model inputs are around this center here, which we can assume that they are. So we're going to see a significant drop in performance if there is concept drift of almost any kind. So this is something that we really need to be wary of. And if we can measure it, capture it, quantify it, and then resolve it, we should do it as much as possible. So again, just to formally define what concept drift is, it's a change in the relationship between the target and the model inputs. So it's a conditional probability of the target given model input distribution. And now I just have a kind of dense kind of summary page that delineates the differences between the concept drift and the covariate shift. So that should be drift here. Let me fix it right now. And again, I already defined those, so I'm going to skip it, and I gave the formula. When it comes to impact on performance, that's one thing that bears repeating. Concept drift will almost always have a negative impact on your performance. Covariate shift may or may not actually have a negative impact on your performance. It might have no impact whatsoever, or it might, in edge cases, actually a positive impact on your model performance. Imagine that your data drifts away from the class boundary. So you have some kind of reasonably well-defined class boundary, and the data moves away from that region. That means that the data has become more linearly separable, and it's actually easier to make predictions on that data. So we're going to expect an increase in performance, whatever metric you use to measure your performance. When it comes to when we expect to see either concept drift or covariate shift, for concept drift, we expect it to see in use cases where the data is not strongly informative. So in other words, if you use some kind of metric like, for example, ROC AUC, we expect that if ROC AUC is generally speaking low, or in absolute terms low, like around 0.5, 0.6, maybe 0.7, we expect to see quite a lot of concept drift. Whereas we expect to see covariate shift for use cases where you have very strong informative data and you can predict the target with high degree of certainty. The reason for that being is basically if the data is very informative, then almost any change that has to do with features that are informative of the target is already one of the features that we have access to, because we have access to almost all the features that have relevant information about the target. Whereas if there's some feature that we don't observe, we don't have in our data set, and this feature drifts, we're going to observe it as concept drift. So if there's not a lot of information in the data, concept drift will happen more often. When it comes to detecting concept drift and covariate shift, we do require targets for detecting concept drift, because if you just look at the formula, you do have the target here. So we need to use the target to really validate whether this pattern has changed in time. For covariate shift, we are only dealing with the distribution of the x's, the features, so we don't need to have access to targets. Now, how can we actually quantify its impact on performance? So we have a couple of algorithms here. For concept drift, we have our reverse concept drift algorithm, which is kind of the main topic of today's presentation. For covariate shift, we came up with a couple of algorithms. We invented CBP and MCBP, and we're also implementing importance weighting, which was discovered by, forgot the name of the university, but the researchers in 2019, and we're going to be implementing that very soon in our open source library as well. And when it comes to measuring the magnitude, interestingly, we're using the same algorithm as for detecting concept drift, RCD, which is available in our cloud product. Whereas for covariate shift, we're going to be using either the univariate drift detection methods, such as Jensen-Shannon distance, or any of the statistical measures, such as KS, Kolmogorov-Smirnov test, or chi-square tests, or when it comes to distance measure, we also have, like, I think 5 other ways to do it. Wasserstein distance is there, etc., etc. And we also have 2 multivariate drift detection methods. We have the drift reconstruction error and domain classifier, which is a new method that we just released, I think, like 3 days ago. So do check it out. There's just a new release with quite robust multivariate drift detection method called the domain classifier. And I'm going to be talking about it soon. But now let's get to the main course of the webinar, which is the actual algorithm called reversed concept drift. What can we use it for? So we can use it to do 2 things. We can either estimate the magnitude of the change in the concept, or we can estimate what is the actual impact of this concept change on the performance of our model that we have deployed to production. So to give you an example of how concept drift actually looks like, imagine that we have our familiar feature X here, and what we're trying to predict is feature Y, but to be more specific here, the feature Y is binary, of course, and we are trying to, apart from just being good at predicting it, we also want to actually correctly predict the probability that feature Y is 1. And we see that beforehand, the original concept that we trained our model on was this kind of sigmoid curve, which was centered around, I would say, 0.0, so exactly in the middle here. And in time, this curve for one reason or another has shifted to the right. And now we will see that the ideal prediction for, let's say, value 0.5 used to be almost 1. Almost all the data points were already positive class, whereas now almost all data points for prediction for input feature equals to 2.5 is going to be 0 or close to 0. So we see that the model will really badly mispredict on any features or any model inputs that are sampled from that region where the concept has changed. And we are trying to, first of all, somehow quantify how big that change is, and secondly, quantify the impact of that change on the expected performance of the model. How can we do it? So first, we need to assume a couple of things. First of all, we're going to assume that there's no covariate shift. Later on, we're going to be able to slightly relax this assumption, but the way we're going to be looking at the result is always with the assumption that there is no covariate shift, even though the algorithm will work perfectly fine, even with presence of certain types of covariate shift. Then the second assumption is that we're going to be looking at specific batches or chunks of data that we're going to try to evaluate whether there is some concept drift or not. So imagine that you deploy your model and you want to, for every day, measure whether there's concept drift or whether there's no concept drift. This is our chunk, so we can chunk our data daily. If we don't care about any specific time period, we can also just say that for every, let's say, 10,000 new data points that comes in, I'm going to batch those 10,000 data points, and I'm going to measure whether there is whether there is a change in concept of that 10,000 data points compared to my reference data, which, for example, can be the test data. So as we look at our monitor data, the data that we monitor, we're going to split the data into chunks. And this chunk size needs to be big enough so we can actually learn the concept that exists on that chunk of data. In practice, it means that basically we need around at least 1,000 data points for every chunk of data. So if, let's say, you only get 10 new predictions every day, you might want to not chunk your data daily, but instead of doing, let's say, monthly. So then at least you'll get a tiny bit more data to actually create those chunks. Then the last prediction, which is kind of a the last assumption, which is kind of an obvious assumption, is that the algorithm needs to be able to learn a new concept. We use for our algorithm, we generally use gradient boosting methods, which are quite good at learning any concepts. So as long as we're dealing with tabular data, this assumption is basically always satisfied. Even if we're dealing with non-tabular data, sometimes gradient boosting models are good enough. I'm not going to say that they're good or they're the best, but they are good enough to actually still model the concept reasonably well. Now, how does the algorithm actually work step by step? So what we're going to do is actually quite simple. We're going to train a model on the current batch, or actually, to be more precise here, I have issues with naming, as you can see. We're going to train a model on our current chunk of data. And this is a new model that we're going to train automatically a gradient boosting model on the current chunk of data we have. Then we're going to use that model to make predictions on our reference data, which, for example, can be the test set, but I'm going to again rename it to reference data just to be fully correct, because our reference data doesn't have to be the test set. It can be, for example, first few months of production. And then we can do two things. We can either estimate the magnitude or estimate the performance impact. Let's first go into estimating the magnitude, but before we go there, I'm going to build slightly more intuition about how we actually train these models and what we do with that model in a slightly more graphical way. So what we're going to do is basically we're going to compare the two models. We're going to compare the two models to actually compare two concepts, and then we're going to measure the difference between those concepts, because the underlying assumption is that the model accurately captures the existing concept in the data, so existing pattern that we're trying to learn, that the model succeeds at that task. So we're going to take our model that we trained on our training data, and we're going to make some predictions on our reference data. So again, let's say most of the time it's going to be the tests. Then we're going to take a new model that we trained on the last chunk of data or a chunk of data, And we're going to also use that model to make predictions on the same data, on the reference data. So we're always going to be using the reference data to make the predictions on. And then we're going to compare those predictions. So we're going to compare the predictions that we get on the test set or reference set from the model that we trained on our training data and from the model that we got on our current chunk. And if these predictions are similar, we're going to say that there is no concept drift. If they are different enough, we can then talk about the existence of concept drift, and we can then quantify how strong it is. And then the notion of similar and different, of course, needs to be quantified. So I'm gonna in a second explain how we actually can do it. Let me just give you one final piece of intuition of how it actually works in a kind of real life production setting. So the way we do it, of course, is we're gonna make these comparisons, but we're gonna do it step by step. So for every chunk of data, these chunks actually would be just single data points here. I made them slightly larger just to make the visualization easier. But for every of these data points here, we're going to train a new model. We're going to make predictions on reference data. We're going to compare those predictions with the predictions that we got from the original monitored model. And then we're going to measure, for example, the difference in the F-score we get based on these predictions. And we're going to plot those over time. And if we see that the predictions are getting worse, it means that the concept is changing. And that is kind of the example in the nutshell, the final piece of intuition of how the algorithms work. It's really not that complex. What is interesting, though, is, of course, how exactly we can quantify the similarity or difference in predictions. And now let's talk about how we can do it. First, actually, I really need to watch out what I write here. First, we're going to talk about the magnitude quantification. What we're going to do here is we're going to try to quantify the actual magnitude of the change in the concept. And the magnitude we're going to just define as this shaded area that we get here. So everything that's right here is how we say the concept is different by that much. And this is just the area between those two curves. Here, I'm explaining that only on a simple one-dimensional use case, but imagine that you have 200 dimensions, and then computing that curve can get slightly harder. So here's how we're going to do it. We're going to do it by computing an integral, which de facto becomes a sum, because we're going to be dealing with discrete data points instead of continuous space. But for the sake of correctness, I wrote that here as integral, and this integral is actually reasonably simple to understand. Let me unpack it. So what we're going to do is we're going to look at every point in the model input space. And again, because we're de facto working with a sum, we're only going to look at every data point in the model input space. Now, instead of weighing each of the points in the model input space equally, we want to also take into account this magnitude with respect to where the density of the data. So if there's a region where there is really a lot of data points, and there is a bit of concept drift there, we would intuitively say that there is actually more magnitude there. Even if there is small change in the concept, it matters more. So we want this magnitude, this metric that we are coming up with now, to matter more. So what we're going to do is we're going to look at the density of the model input distribution in that point. And the easiest way to do it is just to calculate this sum for every data point in model input space on our reference data, because then we're implicitly taking into account the density. There's a lot of data points close to each other. We're going to take each of those separately, and we're going to sum it up, so they will be represented more than the regions in space where there is very few data points. And so this is the P over X part. And then the last part here is literally just what you see on the side. So it's going to be the absolute difference between the probability of target conditioned on where it is in space minus the probability of the alt of the y given the features vector for the reference model. So we're going to look at the original monitored model and the new concept, the monitored chunk. So we're basically just going to take this point here and subtract it from this point here. We're going to take the absolute difference. So if there is a change in concept, it's always going to be positive, no matter where the concept goes up and down. We're going to multiply it by every data point that we see in the reference space, and that's how we get our sum. And this is this value. So that's basically the metric in a nutshell. Now, how it works in practice. So as I already mentioned, we're gonna train a new model for every chunk of data. So each of these points here actually corresponds to chunk of data. And then we're gonna compute this integral or this sum, and then we're gonna plot it as a time series, because basically when you deploy our models to production, they all behave in some way as time series. If we see concept drift, this concept drift will drift in time. So it makes sense to look at everything from kind of a time-based perspective. And we're just going to measure it. We're going to measure the typical variance in the concept that is just noise, just due to random chance. The concept will be slightly different. It will be captured by the chunk model in a slightly different way. So we're going to see some natural variance in the concept, which doesn't mean that there's actual concept drift. It's just due to random sampling errors or a finite sample size effect that it's not zero. So this, we need to establish this kind of baseline on our reference data, which again might be the tested data, and then we see how it evolves in time. And if there are certain spikes in that magnitude, then we know that something is off. And the next step then is to understand whether it actually impacts performance. So now we can move to the second part, which is where this very nice dark pink slide should have been, which is how we can actually quantify the impact of concept drift on model performance. So to build an intuition here, what we're going to do is we're going to try to reconstruct confusion matrix of our model. So again, binary classification. And what we're going to do is we're going to use two models. We're going to use our user model or the monitored model to get the predictions. And then we're going to use our new concept as a proxy for the actual labels. Of course, we could directly use the labels, but it makes sense to use the actual the model, because we're going to be evaluating that model performance on the reference dataset. Remember, we're always comparing everything to the reference dataset. And we will not have the labels for every data point in the reference dataset, because the reference dataset might be distributed differently than our current chunk. So we cannot just take the predictions from the current chunk and say this is the prediction for the reference. We need to have some way that gives us a meaningful prediction for every data point in the model input space. That's why we need to train a new model to capture this new concept. So what we're going to do, we're going to walk step by step of how we actually reconstruct this confusion matrix. So first of all, we're going to make a positive prediction. Let's assume that the user model just makes a positive prediction. That means that we already know that it's not going to be either true negative or false negative, because the prediction was positive. So far, so good. Now, what we're going to also leverage is we're going to assume that this new concept was correct, because it's the only assumption we can make here. And we know that the new model predicts probability of 0.7. Given that this probability is well calibrated, etc., it represents actual probability, we can then say that in expectation over sufficiently large sample size, that's why I mentioned at least 1,000 data points in a while, we're gonna put 0.7 here, because this is the expected value of true positives given that data, given that the prediction was positive, and the new concept is 0.7. So we're kind of evaluating the original model predictions on a reference data set under this new concept. So we're quantifying how the model would have behaved under the new concept that we are capturing and measuring with the new model. But we're still evaluating the actual user model, the original model that we're using to make predictions that are in production. So now we put 0.7 here. This is the expected value of true positive for a certain prediction on reference data under the new concept from the current chunk, using the monitored model, the original model that we deployed to production. And we put 0.3 here, because if it's not a true positive, then it needs to be false positive, and this needs to sum up to 1. We're going to do it again. Let's say that for the second prediction, the model on the reference data predicted 0, new concept predicts probability 0.4. So we're going to put 0.4 here as a false negative and 0.6 as a true negative, etc., etc. We're doing that for the third prediction, and we continue doing that until we get enough data points, ideally around 1,000, and we have this de facto expected confusion matrix. And then what we can do it is that we take that and we can calculate approximate expectation of basically any metric that's based on the confusion matrix, such as accuracy or any other metric you want. Here, for this example, we only have 3 data points, but in reality, we would have more. And we know how the model would have performed on reference data under a new concept. So assuming the new concept that currently exists in the last chunk of data. And this tells us basically how the model would have performed under new concept, and we already know how the model is performing on the reference data. So we can just compare those two, and we're gonna be able to see what is the impact of concept drift on model performance, which is precisely this equation. So what we are calculating for performance impact estimation is the expected value of the performance change given the new concept, which is just the change in the expected value of the original model performance under the new concept and the expected value of the original model performance under the old concept that exists in the reference dataset. So how do we do it? We already mentioned how we calculate the new concept, and the old concept we're gonna do exactly the same way, but instead of putting the new concept here, we're just gonna put the old concept, which, if you're familiar with how NannyML algorithms work, how other algorithms work, is basically just equivalent to CBPE on reference data. So we basically take tested performance, we take expectation over that. So we're dealing with estimated results instead of realized results, because then they're slightly less noisy. And we do the same thing for the evaluation under new concept. We just subtract those two, and we know what is the expected change in performance due to concept drift. How does it look like? And then in a second, I'm going to talk about the limitation and why it's so useful. So we see that if we look at the magnitude estimation that I already showed, it goes up in time. And just looking at the screenshot from our cloud product, we see that F1 delta, so change in F1 due to change in the concept. We see that it's also dropping. We also have some kind of confidence bands here that tell us whether we should trust our predictions or not, which are based on the size of the sample. So even if you cannot get to this 1,000 data points per chunk, you will still be able to get some information, and you will know how strongly trust your predictions, because we have these confidence bands. I can talk about the confidence bands later on if there's questions about it. But now we see that as the magnitude of the concept drift increases, we see expected drop in performance, because if there's concept drift, generally performance will drop. But if you look closely here, it doesn't really follow one-to-one. So we cannot just use magnitude estimation as kind of the only metric we want. If we're interested in change to F1, we actually need to look at the performance impact estimation on F1, because if you look specifically here, you would say that there is very strong concept drift, but the performance is kind of recovering. It hasn't dropped very strongly for that specific chunk. And then you can actually use that, because if you look at this data point here, if you retrain the model, what you would expect is that the impact of concept drift will kind of disappear. So you stand to gain around 0.07 F1 from retraining, which is very useful, because then you know whether it makes sense or whether it's worth the candle to actually train your model, or whether the drop is small enough that retraining might not be warranted, because retraining might be expensive. It might require a lot of cloud resources. It might require a lot of paperwork, bureaucracy, etc. So that gives you an actionable information of whether you should retrain your model or not. Before we start talking about retraining, I already started talking about retraining, but before we continue talking about retraining more, there is one interesting limitation as I wanted to talk about, which is the impact of covariate shift. And there is a very specific type of covariate shift that will make the reverse concept drift detection actually fail in a very interesting manner that we discovered. So just first of all, a caveat is that concept drift detection should work under most forms of covariate shift, even if they are reasonably strong, but it's not guaranteed. And why it's not guaranteed? Imagine that we have some kind of true concept. So the pattern that exists between the feature and the target, and we're now familiar with one feature X and the probability of feature Y. And this is the true concept that exists in reality. We get our distribution of our one covariate X, and we're going to train a model. Let's say anything like an SVM. And we train this concept basically perfectly because we have enough data. Each of the data points that basically exist in the space is reasonably well represented, more represented in the middle, but we have enough representation to actually learn the concept. However, if we observe very strong covariate distribution, so that it used to cover a wider region, but now covers significantly smaller region, what might happen is that even though the concept has not changed at all, so it's exactly the same concept as before, only I copy-pasted the picture in a different way, we will see that when we learn the concept, there is no data here whatsoever. So the model does not learn that there is this kind of, in a way, bimodal distribution that is more likely that's class 1 here and again here. Instead, it learns this monotonic relationship because there is no data to talk about this point. So that way, we're going to not learn the correct concept. We're going to learn simplified or overly simplistic concept because we can only learn from the data that is available in a given chunk. And that means if our chunks are small enough or they do not represent the reference data well enough in terms of how they cover the reference data model input space. That was a mouthful. So where the reference data is distributed, we will not be able to use concept drift to its full potential, and we might either overestimate or underestimate the impact of concept drift on performance, because we might notice that there is some concept drift, or might think that there is some concept drift when there is no concept drift, like here. So that's the limitation. Now let's talk about the most actionable part, which is the concept drift and model retraining. How can we leverage concept drift to actually retrain our models? So imagine that we have a model that we deploy to production, let's say the churn model, and we start measuring concept drift. On the left side here, we see the reference data, and on the right side, we have the analysis data or the monitor data. And we see that there's maybe some small chunk, a lot of weird stuff going on in the first chunk, but we see also that the confidence band is huge. So we're actually not sure whether there is a drop in performance. Maybe that was just a very small chunk. As I mentioned, if the chunks are small enough, we cannot trust fully, and we know we can trust because the confidence band is huge. And then we see that for the first few months, everything is fine. But come March, maybe April 2019, we see a significant drop in performance due to concept drift. So our performance impact estimation of concept drift shows that F1 dropped by approximately 0.05, which is worrying because we don't want basically any drop that exceeds, let's say, 0.01. And when we look at the realized performance, we do see that indeed the drop is in reality slightly lower than 0.05, let's say 0.04, but the model was able to cut, or we were able to actually quantify that the concept drift is almost fully responsible for this drop in performance. So then what we can do, we can look at it and say performance dropped as much as concept drift indicates that it should have dropped, which means that we can fully attribute change in performance to concept drift, which means that we can just use retraining to solve the problem. How can we do it? So first, let's think about why do we actually need to retrain when there's concept drift. So concept is what we train our model to capture. It's this pattern that we want our model to capture. So if there is a change in that pattern, it means that there is a change in the concept that our model was trying to learn. So it's no longer a relevant concept that the model has learned. So we need to retrain it. But so we have our RCD, reverse concept drift detection. We detect concept drift, we trigger retrain. We retrain our model over here. Then we need to make sure that the retraining was actually correct, because there's a million different things that can go wrong when we train our model. Maybe there's some data quality issue, maybe there's strong covariate shift, etc., etc. So we need to validate whether performance is still good. We can use our performance estimation algorithms for it. And the reason specifically I mentioned performance estimation here as the best way to validate our models is that we could technically just wait for more data and use realized performance, so just measure the performance, but we can use estimate performance immediately after we train our model, and even if we use all our data to retrain our model, because MCBP does not need the labels, it only needs model input. So as new model inputs come in, we don't have to wait for the labels, for the targets. We can immediately estimate the level of performance. And if level of performance after retraining is satisfactory, then we can actually deploy it to production. So this should be done in some kind of sandbox environment. We don't deploy the model yet to reduce the risk that the model is actually much worse than it used to be, which is possible and has happened a lot with our users. And then we deploy our model and we continue monitoring. So that way we have this kind of automated trigger for retraining, automated validation, automated deployment, given that everything is fine. And I don't advocate to fully automate everything. In theory, it's possible, but this loop is already much better and much more robust than just automatically retraining, let's say, every week or every month, which is something that some of you might do now. So we retrain our model. And how does it look? So if you look at it, we're going to see that there is certain drop in, so there is certain concept drift. And now we're going to retrain our model on the data from around here. And then we're going to deploy it on the future data. So we need to kind of extend this period. And we see now that there is no concept drift. It basically hovers around 0. So we're able to actually accurately capture the new concept after we retrain the data on all historical data. So we don't need to only retrain it on just the new concept, even though somehow and sometimes this might be better than retraining on the entire data set. But I'm not going to go into details here because that's another half an hour, 1 hour of workshop to decide when to on what data you need to retrain your model. So let's say that we're going to retrain on all our past data, including the new data of concept drift. And we see that the concept drift has been resolved. And again, same thing here. We see that the model performance has reasonably increased. There is some drop here, but that might be just stochastic drop because we don't really know what is the size of the chunks here. And we see that there was significant drop here that there was then resolved with retraining. So retraining based on concept drift generally works. And especially if we can validate that it works, then we have automated, as already mentioned, automated system for retraining our models, validating it works, deploying to production, and continuous monitoring. And that is really it. Before I wrap up, I have a couple of conclusions. They're quite simple. Just to summarize what we discussed so far, there are two main causes of machine learning model failure: the concept drift and covariate. Concept drift generally almost always leads to drop in performance, which is one of the reasons we should really try to estimate it and quantify it whenever possible. It generally happens in models that perform in absolute terms not that great, so raw KC around 0.6, whereas covariate shift may or may not have negative impact on performance, and we should be able to quantify that even without targets. We can quantify the magnitude of concept drift and its impact on performance with our algorithm reverse concept drift. And we need to, however, watch out for specific kinds of covariate shift, which might decrease the efficacy or usefulness of the RCD, especially if the data distribution of the current chunk is much smaller, much narrower than the data distribution or the data coverage we had in our training data. And the last thing, and really most important and most actionable, is that concept drift is a perfect trigger, direct trigger for retraining. It's even better than realized performance because realized performance can also drop because of covariate shift. And if we retrain our model, and the only change is that the data distribution is now different, we will not see increase in performance. We're going to be wasting our time and money by retraining unnecessarily, and additional risk because retraining is always a bit of